Greetings, everyone. Learning is a hobby here. I wanted to go over section 1.3, the exercises, for the video that I just posted the summary for. Let me bring up my the exercise set here with my solutions. We're lucky here in that if you watch the first video that I did on this book by Stillwell a long time ago, I actually wrote up some nice solutions to chapter 1. So back when I had more patience, I actually typed this up in Word. So we have a nice typed out solution document to look at here. So let's go through the problems. So these are the solutions to section 1.3 exercises. So he starts with saying this here, the parameter t in the pair 1 minus t squared over 1 plus t squared, comma 2t over 1 plus t squared, which is the rational point on the unit circle. That's the formula for it that we found in the section 1.3 in the summary. This runs through all rational numbers if t is p over q, and p and q run through all pairs of integers. So here's the first question, 1.3.1. Deduce that if ABC is any Pythagorean triple, then A over C is p squared minus q squared divided by p squared plus q squared, and B over C is 2pq divided by p squared plus q squared for some integers p and q. So here's a solution. This exercises here are relatively straightforward, but let's go through them. So here's the solution. If A, B, and C are a Pythagorean triple, then A over C, comma B over C is a rational solution to the equation for the unit circle, right? Because A squared plus B squared equals C squared, then you just divide both sides by C squared, and then factor out the common power of 2, and that shows that you get a solution to the unit circle. And these are ratios of integers, so they're rational. That implies that there exists P and Q in Z, such that T is P over Q. And if T is P over Q, then just plugging in P over Q in for T in the formula, we get 1 minus Q squared over P squared divided by 1 over Q squared. Sorry, 1 plus Q squared over P squared, and then just simplify the complex fraction by multiplying the top and the bottom by P squared, and you get that A over C is P squared minus Q squared over P squared plus Q squared, and then same thing for B over C. So plug that plug Q over P in for T in the y coordinate for in the formula that we have above. Then B over C is 2 Q over P divided by 1 plus Q squared over P squared. And again, just simplify the complex fraction by multiplying the top and the bottom by P squared, and you get 2pq divided by P squared plus Q squared, and that's it. Well, it's basically just an algebra problem. Okay, use exercise 1.3.1 to prove Euclid's formula for Pythagorean triples, which is something we did in, when did we do that? I think it was section 1.2, which is in a previous video. So we want to use this result that we just derived to prove Euclid's formula for Pythagorean triples. Okay, so if A, B, and C is a Pythagorean triple, then by the previous exercise, there exists P, Q, and R in Z, so integers, for which A over C is given by the formula from 1.3.1. And then you just multiply by R over R, which is like multiplying by 1. That doesn't change anything. And same thing for B over C. You just use the formula from 1.3.1 and then just multiply by R over R. And then that should be a solution to the unit circle. So just plug those values in for X and Y. And then you multiply through by the common denominator squared, which gives you Euclid's formula. So that gives you P squared minus Q squared times R all squared plus 2pqr all squared equals P squared plus Q squared times R all squared. If you recall from section 1.2, that's Euclid's formula. So A is this number, B is this number, and C is this number. All right. The triples A, B, and C in Plimpton 322 seem to have been computed to provide right-angled triangles covering a range of shapes. Their angles follow an increasing sequence in roughly equal steps. This raises the question, can the shape of any right-angled triangle be approximated by a Pythagorean triple? Plimpton 322 is the we talked about that in section 1.1 and 1.3, so you could look back at what that is if you watch that video. So here in 1.33, they want us to show that any right-angled triangle with hypotenuse 1 may be approximated arbitrarily closely by one with rational sides. So here's the proof. So let x, y be a point on the unit circle that is not rational, and we want to show that we can approximate it by rational points. Then there is a real number t such that t is the slope of the line segment containing -1, 0 and xy. So here the slope t is not rational because the line doesn't pass through a second rational point. See figure 1.6 below. That's this one here. So again, we're referring to this line here that passes through P and Q. Okay. Then for any P in N, so any natural number P, and T in R intersect the interval -1 to 1, there exists a smallest natural number Q, such that Q is less than or equal to P times absolute value T, less than Q plus 1. That's because T is irrational. Where it lies between two integers. P times absolute value T lies between two integers. Sorry, natural numbers. Then if you divide everything by P, you get the inequality that 0 is less than P or Q over P is less than or equal to absolute value of T, less than or equal to Q plus 1 over P, which is less than 1. And as P increases without bound, if you take the difference of Q plus 1 over P minus Q over P, that's equal to 1 over P, and if P increases without bound, that ratio goes to 0. Therefore, the absolute value of T can be approximated arbitrarily closely by a sequence of positive rationals. So without loss of generality, that means that if we assume T is greater than 0, we can say without loss of generality, because if T is less than 0, that would follow from symmetry of the unit circle. Let R equal Q over P, then by what we just said in the previous paragraph, R is less than T is less than R plus 1 over P. And then you just get these inequalities here by, plugging in, manipulating the inequalities, right? In other words, R squared is less than T squared is less than R plus 1 over P squared, et cetera, using properties of inequalities. You get that 1 minus R squared over 1 plus R squared is greater than 1 minus T squared over 1 plus T squared is greater than 1 minus parentheses R plus 1 over P squared, et cetera, And same thing for the second number here. This is between 2R plus 1 over 1 plus R squared and 2 times R plus 1 over P divided by 1 plus, in parentheses, R plus 1 over P squared. Okay, so that means that, as long as we let P go to infinity, right, if we let it grow without bound, then the upper and lower bound get closer and closer to each other, which squeezes this number in between them. And the upper and lower bounds for each of these expressions are rational. So therefore, xy can be approximated by 1 minus R squared over 1 plus R squared, comma 2R over 1 plus R squared. This is a rational point on the unit circle to any degree of accuracy that one pleases by just choosing the denominator P large enough. Right? So we can approximate basically any right-angled triangle with a rational right-angled triangle. All right, last question here. Some important information may be gleaned from Diophantus's method if we compare the angle theta equal QOR, that's this angle here. So he's referring down to this picture here. Let me highlight. What color should I use? I'll use black. So what was it? QOR. That's this angle here. I'll call that theta. in figure 1.4 with the angle QPR. That's this angle here. I'll call that alpha. The two angles are shown in figure 1.6, and hopefully you know from high school geometry the relation between them. The relationship between them is that theta is 2 alpha, or if you prefer, alpha is theta over 2, if you remember from high school geometry. Okay, so using this figure 1.6, show that, this is the question here, use figure 1.6 to show that t equals tan theta over 2. So they're talking about the slope of the line here between that passes through P and Q, and that cosine theta is 1 minus t squared over 1 plus t squared, and that sine of theta is 2t over 1 plus t squared. Right, so here's my proof. So let angle QOR be the angle theta. Line segment OQ, so O is the origin. Line segment OQ has length 1 since it's a radius of the unit circle. So that means triangle QOR is a right triangle with a hypotenuse of unit length, with RQ opposite to OR, adjacent to the central angle theta, which means that cosine theta is OR, which has coordinates 1 minus t squared over 1 plus t squared. And sine theta is the length RQ, the vertical side, right, is 2t over 1 plus t squared. Also, angle QPR is theta over 2 by that geometric theorem that from high school that he mentions. And if you take tangent of theta over 2, that's equal to, just from the picture, length RQ divided by 1 plus length OR. And because of the coordinates that we just found, RQ is equal to the value 2t divided by 1 plus t squared, divided by, and 1 plus length OR is equal to 1 plus 1 minus t squared over 1 plus t squared. If you simplify that, you get 2t over 2, which, you cancel the common factors of 2, which gives you t. So that shows that tan theta over 2 is equal to t, and that proves the theorem. Okay. So I think that's it. Yeah, that's the last exercise here. All right, guys. I am going to try and post the summary for some of the sections in this other book by John Stillwell today, Elements of Number Theory. So take a look, keep a lookout for that, and the exercise sets for those sections that I'll post as well. So I'll see you guys in the next video. Until that time, keep learning, and I'll see you in the next one.